In this lecture, we will encounter displacement vectors and define two new operations on vectors, the dot product and the cross product. We will also look at how these operations inform us about some geometric properties of the vectors involved. When dealing with vectors in the coordinate plane, so far we have only considered those whose tails lie at the origin. In general, the vector from point A to point B is called the displacement vector from A to B. If we consider the points A and B in relation to the origin, it is possible to describe the vector AB in terms of the vectors OA and OB. Notice from this diagram that OA plus AB equals OB. So we can write in general that the displacement vector AB equals OB minus OA. Notice that to find the displacement vector, we always subtract the position vector of the first point from the position vector of the second point. For example, consider the points A at -1, 3, 5 and B at 2, -1, 4. We are asked to find the vector AB and the distance from A to B. The displacement vector formula says that AB is OB minus OA, so we want to find 2, -1, 4 minus -1, 3, 5. This resolves to the vector 3, -4, -1. To find the distance between A and B, we can use the length formula on the vector AB. So the length AB is given by the square root of 3 squared plus -4 squared plus -1 squared. This results in a length that is the square root of 26. The displacement vector diagram naturally forms a triangle, so this might motivate us to apply the cosine rule to this triangle. Let's consider two two-dimensional vectors A and B, and let's denote by theta the angle between them when their tails are touching. If the components of A are given by A1 and A2, and similarly B1 and B2 for B, then the displacement vector B minus A has components B1 minus A1 and B2 minus A2. Using the cosine rule on this triangle, we have that the length of the displacement vector squared equals the sum of the length of A squared, the length of B squared, and the length of A times the length of B times cos theta. We can rewrite this in terms of the vector's components, using the vector length formula. Expanding out the brackets and collecting like terms, we eventually reach the result that A1b1 plus A2b2 equals the length of A times the length of B times cos theta. This simple expression actually has a special name, the dot product of the vectors A and B. Let's now formally define the dot product of two vectors. We will write the operator as a raised dot and call the expression A dot B. Our geometric definition for the dot product is that A dot B equals the length of A times the length of B times cos theta, where theta is the angle between A and B. Algebraically, the dot product of two vectors is the sum of the products of their corresponding components. That is, in 2 dimensions, A dot B equals A1b1 plus A2b2. In 3 dimensions, A dot B is A1b1 plus A2b2 plus A3b3. Note that the dot product of two vectors gives a scalar, not a new vector. Note also that if A dot B equals 0 and neither of the vectors is 0, we must have that cos theta equals 0, which means that theta is pi on 2 radians. So we can conclude that for non-zero vectors A and B, the statement A dot B equals 0 is equivalent to saying A is perpendicular to B. For example, we might be asked to show that the two vectors A given by 3, 4, 1 and B given by -2, 1, 2 are perpendicular. We can calculate the dot product by taking 3 times -2, 4 times 1, and 1 times 2, and adding all these together. The result in this case is 0. Since neither A nor B is the 0 vector, but A dot B equals 0, we can conclude that they are perpendicular. We could also be asked to find the angle theta between two arbitrary vectors. For example, A given by 1, -2, 1, and B given by 2, -3, -1. Let's again start by finding the dot product. In this case, A dot B turns out to be 7. We should also find the lengths of A and B using the length formula, which in this case gives that the length of A is square root 6 and the length of B is the square root of 14. Putting this all together, we know by definition that A dot B is the length of A times the length of B times cos theta. So rearranging and substituting the values already found tells us that cos of theta is 7 divided by square root of 6 times square root of 14. This gives a value for theta of about 40 degrees and 12 minutes. Another useful vector operation is called the cross product. This operator is written as a normal multiplication symbol and pronounced A cross B. The cross product is only defined for three-dimensional vectors, and algebraically, A cross B is given by the rather complicated looking result shown here. The first component of A cross B is A2 times B3 minus B2 times A3. Notice this term uses all components except A1 and B1. Similarly, the second component of A cross B is A3B1 minus B3A1, and the third component of A cross B is A1B2 minus B1A2. Special care must be taken with the order of the pronumerals here, because confusing the signs involved will produce an incorrect result. Geometrically, it turns out that the length of A cross B equals the length of A times the length of B times sine theta, where theta is the angle between A and B. Note that the cross product of A and B gives a new vector. The direction of the vector is always perpendicular to both A and B. Note also that if A cross B is 0 and neither of the vectors is 0, then we must have that sine of theta is 0, and so theta is 0 or pi radians. So we can conclude that for non-zero vectors, the statement A cross B equals 0 is equivalent to saying that A is parallel to B. Finally, another geometric interpretation of the length of A cross B is that it is the area of the parallelogram spanned by A and B. We can see this is true because the formula is twice the area formula for a triangle. As an example, let's calculate the cross product of vectors A given by 1, negative 2, 3, and B given by 2, 1, negative 1. The first component is given by negative 2 times negative 1 minus 1 times 3. The second component is given by 3 times 2 minus negative 1 times 1. And the third component is given by 1 times 1 minus 2 times negative 2. So altogether, we find that the cross product is the vector negative 1, 7, 5. We could also be asked to show that two vectors are parallel. For example, consider the vectors A given by 2, negative 3, 9, and B given by negative 4, 6, negative 18. Suppose we would like to show that they are parallel. If the cross product of the two vectors is the zero vector, then we can conclude that they are parallel. So calculating the cross product as before, we find in this case that A cross B is indeed the zero vector. Since neither A nor B is the zero vector, and A cross B equals 0, we can conclude that they are parallel. As an alternative approach to the previous example, we could instead show that the two vectors are parallel by using our original definition of parallel vectors. Recall that two vectors are parallel if one is a scalar multiple of the other. In this case, we can see that B is in fact negative 2 times A. So this is another way to conclude that A and B are parallel. In summary, we have seen how to find the displacement vector between 2 points, and to find the dot product and the cross product of two vectors. We have also seen how the dot and cross products can be used to determine properties of the angle between the two vectors.